Everybody knows about, we've got pressure, volume, temperature. We've talked about those. And everybody has learned about the so-called ideal gas law. Right? Which is pressure times volume is equal to the number of moles in the system times the universal gas constant times absolute temperature. That's absolute temperature in Kelvin or Rankine. The universal gas constant this is the moles of the gas, the amount of the gas, and pressure and volume are okay. All right? Of course, in petroleum, we have to say this is absolute pressure. We don't want to use this equation with pressure PSIG, or, okay? So, anybody not familiar with this equation? So for SI units, pure SI units, pressure in Pascal, volume, cubic meters, temperature, Kelvin, and moles in, because a mole is what? A mole of material does anybody know the molecular weight of air? 28.97. 29, close. 28.97. Air has got a bunch of stuff in it. Pure methane, that's the most abundant hydrocarbon on Earth. Pure methane, anybody know the molecular weight of that? About 16.04, da 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 da. But what does that number 16 represent, or 28.97? What does it represent? Let's take 16 for molecular weight of methane. It is 16 grams, put it on a weight, 16 grams per mole, little mol. Okay. So the molecular weight of methane, we write it C1 or CH4, one hydrocarbon, 16.04 grams per, and the SI unit of moles is well, it's actually not, it's not mole, I won't say SI, but it's grams per little mol. Okay? But that's also equal to 16.04 kilograms per what? Per 1,000 kmol. Okay? Which is equal to 16.04 pounds mass per what? Is called pound mole. Okay? People don't use this, but you can use any mass units. Ounces per ounce mole. The point is that the mole as a quantity is associated automatically with the mass unit that you want to use. And to be, if you just write mole, you don't know what 16 represents. Okay? So you have to be careful. And to be careful, this is not SI, but this is being careful as engineers. You always attach a mass unit with the MOL. Not K, but kilogram. Pound mole, osmole, gram mole. Because if we're selling 62 million gram moles per day of oil, we want to be able to figure out how many barrels that is. And if you just say 16,000 moles per day, I have no idea how many barrels per day. I can't quantify it. I can assume, oh, he means gram moles. She means gram moles. Well, maybe not. So you have to associate a mass unit with the mole. Okay? So what I'm going to do here, the SI unit for mass is kg. So this is going to be kg mole. This is going to give us, this is pure SI. Okay, that's pure SI. Now the question. What is the value of R, the universal gas constant, for this set of units? 8.14. Anybody disagree? I didn't learn the number in school. Huh? No, it's not unitless. It has these units. Pascal, cubic meters, Kelvin, kilogram mole. 8. How many want to bet me a pizza that you're wrong? Yeah.
I think it's joule per kilogram per mole.
You think it's what?
Joule per kilogram per kilogram.
Okay, we don't want to get into joules. You can also express it in joules, but I don't. Huh? It doesn't. It doesn't have units? Okay. Somewhere down here. There's a table in this appendix that gives us the universal gas constant for different sets of units. I can eat pizza for a year, right? What's the number? Kilogram, we got Pascal, cubic meters, Kelvin, kilogram, 8314. That's the SI, at least if you use the pure SI units. You guys were cheating, you were using grams there. Okay, so it's 8314.3. Okay. So now I want us to do an exercise where you convert I want you to convert. Everybody has a cell phone, right? Somebody not have a cell phone? In the old days, I was so frustrated because I came to Norway and calculators, programmable calculators. I came to Norway before they had personal computers. Yes, before we had any computers, almost. I mean, with a screen, we didn't have computers with a screen. Okay, programmable calculators were the big thing. So I walked around with a calculator in my pocket. I mean, I was never without a calculator. And then came to the period of the PCs and everything, and nobody brought calculators to class. So I couldn't have anybody doing exercise. I had to do all the number punching myself. Okay, but now everybody's got a telephone that has a calculator on it, right? So what I want you to do is I want you to find R for my set of units. Okay. So now we'll solve this problem of finding the real gas constant in field units, given that the gas constant in SI units is equal to 8314.3. And to do this, we'll start by writing the ideal gas equation like this, and putting the units like this. The moles has a mass unit, which is kilograms in the SI, and we have Kelvin here. And then this is the gas constant for this set of SI units, which is 8314. Now what we want to do is that we want to input into the ideal gas equation using a different set of units, pressure and PSIA, differentiating between gauge and absolute. We always use absolute. Volume in cubic feet. Mass unit for the mole is pound mass. And temperature in absolute degrees Rankine. Now, what we want to do is we know the equation with the correct constant, 8314, if all of the quantities are in SI units. So what we're going to do is we're going to figure out how to get the SI unit if we input the value in a different unit, which in this case is PSIA for pressure. And to do that, we're going to have to, we've got 14.50377 PSI A per bar. Again, I'm just going to keep that nomenclature of the absolute. And then we've got, to convert from bar, we've got 10 to the 5th Pascal per bar. And basically this entire term here we're going to use up here for pressure in Pascal. We'll just replace that. And likewise for volume, to get that into cubic meters, where we actually input the volume in cubic feet. And we'll use this conversion, 35.31 cubic feet per cubic meter. And on mass, or mole units, we need it in kilograms, but we're going to input it in pounds. So we have to use this conversion, 2.20, I think it was 2.204 pounds per kilogram. And then we've got the final as temperature. We need that in Kelvin. But if we input that in degrees Rankine, then we have 1.8 degrees Rankine per Kelvin. Okay. So then we can just simply substitute each of these terms here into the equation up here using the 8314. So we'll just write pressure input in PSIA times the conversion 10 to the 5th over 14.50377. I'll simplify a bit there, times volume input in cubic feet with the conversion dividing by 35.31, and that's going to be equal to the moles input in pounds, pound mole, with the conversion to kilogram moles with the 2.2 pounds per kilogram mole. And then we've got the temperature, which we're going to input in Rankine instead of Kelvin. And then we have this 1.8 conversion, degrees Rankine per Kelvin. And then we have the SI value of 8314 for the real gas constant. So basically this entire term here is the same as pressure in Kelvin. This term here is the same as volume in cubic meters. This term here is the number of moles in kilogram moles. And this term here is the same as temperature in Kelvin, though we're inputting with our set of field units. So then we can simply write this as pressure in PSIA input times volume input in cubic feet is equal to pound moles and temperature, degrees Rankine. And then we collect all these terms on the right, so which is 8314. We've got the 1 over 2.204. We've got the 1 over the 1.8. And we move from the left side of the equation up here. We get 14.5 divided by 10 to the 5th. And we bring the 35.31 term here. And this entire term here will then represent our gas constant for field units. And that value is basically 10.73. And if we do all the unit corrections exact with all the digits, then I believe this is 10.73146 for that set of units: PSIA, cubic feet, pound moles, and degrees Rankine. Now we can check that in the Appendix A first. So let's go open Appendix A and find the gas constant table here. And we've got PSIA, cubic feet, degrees Rankine, and pound mass, and we see the 10.73 number. You'll also find in Chapter 2 of the monograph, search for gas constant. Let's see here. Maybe it's Chapter 3. you'll actually find the discussion of what we've been looking at here, and you'll actually find an equation with an example showing the way to calculate R for any given set of units relative to the field units, which has the 10.73 number here. So there's an example there, and you could go back through and use your Pascal and Kelvin and cubic meters and kilogram mole, and you could show that we end up with the 8314 number. It also shows you how to convert and using the energy unit, energy, temperature, and mass. So this is a simple example of how, given an equation with a certain set of units in the variables in the equation, if you want to change the set of input values to the variables in that equation, how you can determine the new constant that's required to end up with the correct result.